All right. So before we write a formula for a determinant function, let us prove that no matter what formula you write, the determinant function is uniquely determined, yeah, on the space of n by n matrices. Any function which is alternating, multilinear, and normalized is uniquely determined. This we have proved for 2 by 2. We want to now prove it for n by n matrices. Okay. Now, to prove this, let us first prove this fact that suppose f is a multilinear alternating function. So I'm using only two properties, multilinear alternating function on n by n matrices. And suppose that f on the identity matrix is 0, then f is identically 0. Now, this vanishing lemma you can derive from on 2 by 2 matrices. This 2 by 2 case, what we proved was that alternating multilinear function on space of 2 by 2 matrices is xy xu minus yz times d of e1 e2. So if d of e1 e2 is 0, it will say that any alternating multilinear function is equal to 0. Okay. This now we want to prove for alternating multilinear function on the space of n by n matrices. We already know the proof for 2 by 2 matrices. Let's do that. So display the column vectors of an n by n matrix. Yeah. Then every column vector I can write as a linear combination. So if I write jth column vector, the entries of jth column vector are uh, a1j. Sorry. The the AJ column is A1J, A2J, A. This is a n by n matrix, so A and J. This is the jth column. So I can write the AJ as A1J times E1, then A2J times E2, and ANJ times EN. So I express every column as a linear combination of these basic column vectors E1, E2, En. Right? Now, F is multilinear. So once I write this, each column vector as a linear combination of E1, E2, En, I follow the process that I followed for 2 by 2 matrices and apply multilinear property and alternating property. And finally, I will get a sum where I will have a permutation of E1, E2, En. So this E1, E2, En are coming in certain order, right? They are coming in certain order. You see, for the case of 2 by 2 matrices, yeah, they came in certain order, right? There were so many terms: xe1, ye1, ze2, ye1, right? So e1, e2, e2, e1, then e1, e1, e2, e2. So if I have these n terms, I can have this can be written in n ways. I can choose any ei here. Similarly, here I can put any ej and so on. Okay. So when I expand, once I put each column vector as a linear combination of E1, E2, En, I can use multilinearity, and at the end I get a sum of this type. Yeah. So these entries A2, A1j, A2j, Anj, they will come out of the determinant function. Yeah, f is my multilinear alternating function. F is multilinear alternating function. These entries in the various column vectors will, by multilinear property, they will come out, and we will be left with f operating on a matrix where the column vectors are EH1, EH2, EHn, where h is some function of 1 up to n, right? Some function of 1 up to n. But by alternating property, whenever any of these column vectors are identical, f will be equal to 0 because it's an alternating function. So therefore, we can just focus on the terms which are bijections. Okay, these are bijections. So this H is a bijection of 1 to up to n. Okay. take a bijection of 1 up to n, and then I will get this sum. Okay, so this sum is over all the bijections. Okay, so f is operating on a matrix which is obtained from identity matrix by permuting the column vectors. Okay, now we will apply alternating property, and by exchanging adjacent column vectors, I can convert this into f of E1, E2, En, and there will be some sign here. Because whenever I interchange two column vectors, I acquire a negative sign. So whenever I'm given this bijection, h from 1 up to n to 1 up to n, then doing interchanges of column vectors certain number of times, f of EH1, EH2, EHn can be converted to plus minus f E1, E2, En. Okay. So this is, so my multilinear alternating function, this has any multilinear alternating function is looks like this. So if f of E1, E2, En is 0, then f itself is 0. Okay. So multilinear alternating function which is 0 on the identity matrix is identically a 0 function. That's what we have proved. Okay. Any questions on that? Multilinear alternating function which is 0 on the identity matrix is identically the 0 function. Okay. Now let's prove that if f is alternating multilinear function of order n and d is a determinant function of order n. So f lacks the normalization property, but d is multilinear alternating and normalized. So it's a determinant function. So I have alternating function, alternating multilinear function, and I have determinant function. Then this theorem says that this multilinear alternating function is actually a multiple of determinant function by f E1, E2, En. This we have proved for 2 by 2 case, right? For 2 by 2 case, we proved this formula that this D of A1, A2, An was the determinant of 2 by 2 matrix, and then this was F E1, E2. So this we already did for two by 2 matrices. Now we are doing it for n by n matrices, that any multilinear alternating function is actually a scalar multiple of a determinant function. Okay. So in particular, if f is also a determinant function, then this is 1, and therefore f equal to d. So this is the uniqueness theorem, that we show that any two alternating multilinear functions, they are scalar multiples of each other, and that scalar is the value of the function on identity matrix. So if both the functions are determinant function, then it forces the functions to be same, and therefore uniqueness will follow. That determinant function is unique function. Okay. Let's prove the uniqueness. Okay. We want to prove that any two determinant functions are identical. Okay. So by first proving that any multilinear alternating function is a scalar multiple of determinant function. So look at f of A1 up to An, d of A1 up to An times f of E1 up to En. F is not assumed to be alternating, so f has certain value on identity matrix, and I look at this difference of these two. Okay. F is multilinear, d is multilinear, and this function is a scalar multiple of a multilinear function. You can check easily that scalar multiples of multilinear functions are multilinear. Sum of multilinear functions is multilinear. So this G is multilinear function. Okay. This G is a multilinear function. It is also alternating because f is alternating, d is alternating. So if two column vectors of A are identical, f will be 0, d will be 0, so G is also 0. Okay. So f and d are alternating multilinear, and therefore G is also alternating multilinear. But look at value of G at identity matrix. Okay. If I take the value of G at identity matrix, this is f of identity matrix minus d of identity matrix, that is 1, and this is f of identity matrix. So it is 0. So G is multilinear alternating function, and its value on the identity matrix is 0, and therefore it must be 0 function. Once it is 0 function, f is a scalar multiple of determinant function, and if f itself is determinant function, then this is 1, and therefore f will be equal to d. So uniqueness follows. Yeah, any questions? We have proved that without knowing a formula of determinant function, we have proved that it is unique simply by using the three properties, that any function which is alternating, multilinear, and normalized is uniquely determined, and we know its value on 2 by 2 matrices, and by same technique we can find the value on 3 by 3 matrices. So you should write down, you should derive the formula for determinant of 3 by 3 matrices using the three properties of determinant function. Yeah. So we see we have some question. Yeah. So Vecha Kumar, you are saying that f, d, and g here are functions. Wouldn't they be column vectors in n dimension? No, no. So f and f is a function. F is a function from the space of n by n matrices. F denotes any field of rational numbers or real numbers or complex numbers. So f is a function. D is also a function, and therefore this is a value. This is in f. So G is also a function from the space of n by n matrices. And we are saying that G is identically 0. Okay, G is identically 0 because you can, right, we've proved that if I put E1, if I operate G on identity matrix, it is equal to 0, and it is multilinear alternating, and so G turns out to be 0 by the vanishing lemma, and that shows that f is D. So the determinant is unique. Yeah, Vecha Kumar, is that fine? Okay. Yeah. All right. So let's now look at the existence. We have proved uniqueness. Let's prove the existence. So setting determinant of a 1 by 1 matrix equal to A, you can check that this satisfies the three properties. So 1 by 1 matrices, it is easy. 2 by 2 matrices, we already proved. Determinant function is uniquely determined. It is the usual determinant of a 2 by 2 matrix. Yeah. So we are going to now apply induction on the number of rows of a square matrix to prove that determinant function exists. So we can assume existence of determinant function of order n minus 1 by n minus 1. That is, we know the determinant function on 1 by 1 matrix and 2 by 2 matrix, and you can calculate on 3 by 3 also. So assume that we know what is determinant of a n by n minus 1 by n minus 1 or lower size matrices. Okay. And by induction, we know that it is uniquely determined. Okay. So we are applying induction on the size of the matrix. And we are saying that on up to n minus 1 by n minus 1 matrices, determinant function is determined. Okay. It is already unique, but we are saying that we know the formula already. Now we will derive a formula for determinant of n by n matrices in terms of n minus 1 by n minus 1 determinants. Okay. So let us look at Aij to be the n minus 1 by n minus 1 matrix obtained from A by deleting ith row and jth column. Yeah. So I have this n by n matrix, and I look at ith row and jth column and remove them. Once you remove them, I am left with a matrix of smaller size. It is square matrix. By induction, I know its determinant. Okay, I know the formula for its determinant. Okay, so now we will define determinant of a n by n matrix in terms of these determinants of submatrices. So this is called the expansion by the first row. Okay, this is called the expansion by first row. We can actually choose any row or any column. Yeah? So we are displaying the first row of the matrix, okay, and then expanding using the first row. So A11, take A11 and delete this row, first row and first column. Now the matrix that I get here, submatrix, that we are calling as A11. So I know determinant of A11 by induction. So look at A11 times determinant of A11. Now we look at A12 and repeat this. Remove the first row and remove the second column. I get a submatrix of size n-1 by n-1, and I write A12 times determinant of A12. Okay, and this is alternating sign, so I get -1 to the power n plus 1 A1n determinant of A1n, and so I'm looking at this last entry in the first row, and then remove the first row and the last column. I get the submatrix A1n, and I multiply determinant of A1n with A1n and put a sign. So sign is alternating. We have plus sign here, minus sign here, and so on. Last sign will be -1 to the power n plus 1. Okay. So I'm defining a function. Okay. I'm defining a function in terms of determinants of smaller matrices of order n-1 by n-1. Okay. I want to show that this is a determinant function. Yeah, this is called the expansion by first row. You can take second row or third row or anything. Okay, and we can also take expansion by columns or rows and write down a formula which is simply looks like this. Okay, but to prove that it is determinant, what is our approach? We have proved that determinant function is unique. Okay, to show that this is determinant function, I must show that it is multilinear, alternating, and its value on identity matrix is 1. Okay, its value on identity matrix is 1. Okay. The value on identity matrix is 1. That is quite easy. So if I take identity matrix, is like this. So we are expanding by this row. Only 1 is the non-zero entry. So there will not these things will not contribute. If I take identity matrix, these will not be there. I will just get 1 times determinant of this. But determinant of this n-1 by n-1 identity matrix is 1 by induction. Okay, so f of identity matrix is 1. That is clear. We have to prove these two properties, other two properties. So alternating property. Okay, alternating property. Suppose A has 2 identical columns, AJ and AJ plus 1. Yeah. So these 2 columns are identical, AJ and AJ plus 1. Then I want to show that its determinant, this f of this such a function, such a matrix is 0. Yeah, f of such a matrix is 0. Okay. So if I take such a matrix, let's say I have a 4 by 4 matrix, and second and third column, they are identical. Okay. Then how will f of a look like? F of a will have 4 terms, right? A11, A12, A13, A14. And this second and third column are equal. I want to show that if I apply this formula, I get 0. Okay, I get 0. So let us use this formula to show that this is actually 0. So keep this 4 by 4 matrix at the back of your mind to see what is going on. So suppose that AJ and AJ plus 1, these 2 adjacent columns are equal. Okay. Then I look at the submatrix A1I. A1I, so in this 4 by 4 case, there are 4 such matrices, A11, A12, A13, A14. Okay. So if I look at A11, A11 will be this matrix. I delete the first column and the first row. then this matrix is a 3 by 3 matrix, and original matrix has second and third column equal. So the second and third column of this are also equal. So determinant of A11 is 0. Okay. Yeah. Now the general statement for this, for n by n matrices, that A1I, if I choose the submatrix which is obtained by deleting the first row and ith column, will have equal columns except when I equal to j or I equal to j plus 1. Yeah. So here I was equal to 1 and it was not equal to 2 or it was not equal to 3. Then when I look at this submatrix A11, it will have continue to have two identical columns. So A1I, this submatrix, will have equal columns except when I equal to j or I equal to j plus 1. Because when I equal to j or j plus 1, we will be removing one of these columns to calculate A1j or A1j plus 1. Yeah. So A1j and A1j plus 1 may not have identical column, because one of the AJ or AJ plus 1 will be removed. In this submatrix, jth column is removed. In this submatrix, j plus first column is removed. Okay. But as long as I is not equal to j or j plus 1, A1I will have identical columns, and therefore its determinant is 0. Yeah, its determinant is 0. Okay. So we substitute these values. Yeah. So FA will have only two terms left in this, A1j times determinant of A1j, and this A1j plus 1 times determinant of A1j plus 1, and the sign is here is minus 1 to the power j plus 1, here sign is minus 1 to the power j plus 2. Because the other determinants are all 0. So I have these two terms left over. Yeah. But A1j is the entry in the first row of jth column, and A1j plus 1 is the entry in the first row in j plus first column. But jth column and j plus first column are identical. Yeah. So A1j is equal to this. Okay. This is equal to this. And so AJ is equal to AJ plus 1. That says A1j is AJ plus 1. And also A1j and A1j plus 1, they are identical matrices. Yeah. Because when I remove jth column or j plus first column, I am left with the same matrix. So one of AJ or AJ plus 1 is there in one A1j or A1j plus 1, but they are same matrices. Okay. So these two terms, they just differ by a negative sign, and therefore f of A is 0, and therefore f of A1, A2, An is alternating. Is that clear? So I wrote the expansion of f by the first column, by the first row, and I want to show it is a determinant function. This is determinant of the matrix. To show it is determinant of the matrix, I need to prove it is alternating, multilinear, and normalized. Normalized property I showed. This is the alternating property. Multilinear property, yeah. Multilinearity of f is left as an exercise. You do this. When a equal to I, by induction, f is 1. So you use this formula and please prove the multilinear property. It's a good exercise. Straightforward from this formula that this is multilinear. Okay. Yeah. So we have proved existence of determinant function. This is expansion by the first row, and exactly same proof will be can be written and you can write a formula by expansion by any other row. Okay, any other row and any other column. You have to be careful about the signs. The signs, if I use Aij anytime, then the sign which will go with this will be 1 minus 1 to the power I plus j. So suppose I expand by the second row. Okay, I want to expand by the second row. Then it will be minus 1 to the power the first the entry in the first row and the entry in the second row and first column. Okay, second row and first column. Determinant of A to 1. Then the sign will be 1 plus 2. Then I look at the next entry. Next entry is a 2, 2, and the sign will be minus 1 to the power 2 plus 2, and determinant of a 2, 2, and so on. So you have to be careful about copying this formula for determinant function which is obtained by fixing any row or any column. Okay? The signs matter here. So therefore, we have many formulas for determinant. Okay? But we have proved that determinant function is uniquely determined. So whether you expand by rows or columns, it is the same.